twin spacecraft on a mission to unlock the mysteries of Earth's Van Allen belts.
A planetary enigma in our inner solar system.
Go PSP.
A daring mission to shed light on the mysteries of our closest star, the Sun.
It will be the very first mission to orbit an asteroid.
Spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
All right, so thank you to our day one sponsors, Johns Hopkins University Applied Physics Lab, KBR, and SAIC. So following up on some of what Thomas DeBurkin was talking about, how do we get the information we need to help us understand the Earth's climate better? This panel will discuss the technologies and missions currently assessing the state of our home planet and what kind of information is being collected. This panel is called Eyes Wide Open, Space-Based Observations and Data Collection. Our moderator for this session is Christa Peters-Lidard, the Chief Scientist and Deputy Director for Hydrosphere, Biosphere, and Geophysics at NASA Goddard. Christa, please introduce your panel.
Yes, hi, good morning. And what a great way to start off our planetary stewardship by talking about our home planet, Earth. So we've got four wonderful panelists. The panelists include Doug Morton from NASA Goddard, Tom Neumann from NASA Goddard, Chris Orndorff from Maxar, and Pam Sullivan from NOAA. The way this panel is going to work is that each panelist will give a brief 5-minute introduction to their subject matter, and then we will open it up for questions. So let's get started. First, I'd like to introduce our first speaker, Doug Morton. Doug is an Earth system scientist and the chief of the Biospheric Sciences Lab at NASA Goddard. His research focuses on fires, forests, and food production. Doug, take it away.
Thank you very much, Christa. It's a great opportunity to share some of our latest research and to share the stage with such a wonderful panel to talk about how our space-based observations really do form the basis of our planetary stewardship. And so if there's a chance to bring up my slides, I'm going to dive in and talk a bit about fire. And I think that not unlike our ongoing discussions where everyone has learned a lot more in the last year about epidemiology, it's hard not to think that we are all now better aware of the nature and the characteristics of how fires are changing our planet and how climate change is changing fires. So next slide, please. One of the exciting things about being an Earth system scientist at NASA is the opportunity to use space-based observations to look at every part of the fire science puzzle. And so for me, that's using observations that help us understand the changing characteristics before the fires begin, using information about the three-dimensional structure of vegetation, or using information that helps us understand the localized impacts of drought. Many people are familiar with the fact that space-based observations are often the first to detect new fires in remote regions like the Western United States, the Amazon, or the outback of Australia. And that continues to be one of the most obvious applications of our space-based observations for planetary stewardship. And of course, the wake of those fires, the post-fire environment, really sets the stage for how ecosystems will change in response to fire activity. I'm also actively interested in how we take observations in the atmosphere to track the smoke and the trace gas emissions that are a part of the fire puzzle and that contribute to the global warming problem, and how we can bring all of those observations together into our latest data simulation models to understand, predict, and respond to those changes in the coming days. So next slide, please. This is just one example of how those puzzle pieces all come together. In the central image, I'm showing you a vision from space, the Aquamodus instrument with data over California and the Western United States from early September last year. And you can see those well-defined smoke plumes as fires were burning simultaneously across California, Colorado, and Oregon. On the lower left, you can see how we use those day-to-day estimates of where the fire is to predict and track how the fire is growing and spreading. Really unprecedented fire behavior with rapid fires, spread, and smoke putting communities at risk. And on the lower right, you can see how we took that information about the fires and the smoke from our space-based observations to begin to predict which parts of the country would be experiencing hazardous conditions. In this case, particulate matter, PM 2.5, from the smoke as it settled and spread across our country. And then those photos at the top show you that really over the course of this week, people from coast to coast felt the impact of those fires. The area around San Francisco had unhealthy air quality for more than a month. And even in Washington, DC, where I live, we were treated to spectacular sunsets, but that was a real reminder of the fact that the entire country was experiencing the impact of fires. And as an Earth system scientist, to me, that means fires are changing, obviously, the conditions and the concerns we have for air quality and human health. They're changing the ecosystems where they're burning, and they're changing the atmosphere and the conditions of our planet far from where those fires have started. Next slide, please. Of course, we focus a lot on the California wildfires in a year like 2020 and other places like Colorado, but it's important to remember that we map more than 1 million large fires every year from space. And every one of those fires is critically important to the communities where it's burning, to the ecosystems that it changes, and to the planet in terms of our understanding of how fire in its total impacts our atmosphere, greenhouse gases, aerosols, and the like. So this is a really important compilation of data, which you might have forgotten. The big fires in Australia, or the big fires in Siberia, or the big fires in the world's largest wetland, the Pantanal in Brazil. But we didn't forget those from space. And we've been tracking, monitoring, and assessing how each of those areas are experiencing new and more powerful fires. Just got one last slide that really, I think, drives home the point that it's obviously our real-time observations that give us critical situational awareness, but it's the long record of data from our satellite observations that tell us how our planet is changing. And so this map on the top shows you the amount of area that burns every year. And you'd be right to have your eyes train in on Africa, which is responsible for most of the burning and many of the emissions happening every year. But if you look at the bottom map, you can also see those blue colors showing you places around the world where fires have actually gotten more rare. Fires have declined. And surprisingly, while we talk about how places like California are ever more fire prone, the total amount of burning has declined by more than a quarter over the MODIS data record. And so we're talking about circumstances where savannas, ecosystems that are adapted to fire, are burning less than they ever have before, putting those unique biomes at risk of changing in response to fewer fires, as opposed to more fires that we're seeing in temperate forests and boreal forest regions. And so putting these pieces together really helps us understand the fire puzzle, and space-based observations are really at the heart of each of these aspects. Thanks.
Thanks, Doug. Wow, that's great. I mean, you talk about eyes wide open. I mean, who knew that fires were decreasing in these areas and the impact on ecosystems might be significant. So we'll get back to that when we get to the Q&A session. Thanks. All right, our next panelist is Tom Neumann. Tom is the ISAT-2 project scientist at NASA Goddard and also chief of the Cryospheric Sciences Lab. Tom?
Thanks, Krista. Today, I'm mostly going to be talking about ISAT-2 and the measurements that it takes in support of measuring changes in the cryosphere, but also measuring changes globally. If we could go to the slides. As its name suggests, ISAT-2 was a follow-on to the original ISAT mission on orbit from 2003 to 2009. And ISAT-2 was called for in the last Earth Science Decadal Survey back in 2007 as a high priority. That culminated in a successful launch in September of 2018. We've been on orbit now for about 2.5 years and have collected over 1 trillion elevation measurements globally. Our data is available to the public for scientists and citizen scientists to use through the National Snow and Ice Data Center, and I encourage you to take a look if you're interested. Let's go on to the next slide. ISAT-2 carries a laser altimeter, and what that does is it transmits very weak pulses of laser light in the green part of the spectrum and splits that laser pulse into 6 separate beams and precisely times how long that light takes to go from the observatory down to the Earth and back again. And it's that round-trip measurement of the time that the laser light takes to travel that's the basis of our elevation measurement. The instrument on ISAT-2 sends out 10,000 laser pulses per second, and at our orbital velocity, that results in laser footprints on the surface of the Earth spaced by just 70 centimeters between consecutive shots. So under clear sky conditions, when we're not precluded by smoke or by clouds, we generate really, really dense, long track elevation measurements in each one of these different spots. The other interesting thing to note is that ISAT-2's detectors are measuring individual photons, and it's that individual photon time of flight, which is the basis of our elevation measurements. It's such a NASA thing to do. When we started working on it, I was like, do photons actually exist? I thought they were a theoretical construct to tie the wave and the particle duality of light together. But no, they are an actual thing, and you can use them to measure heights really, really accurately. Let's go on to the next slide and take a look at some of those results. One of the main objectives for ISAT-2 is to measure changes in the great ice sheets in Antarctica and in Greenland. And the figure on the right is an example of a result by combining ISAT-2 data from 2018 and 2019 with data from the original ICESat data from 2003 to 2009. And what we see in this figure in the map of Antarctica is that places like West Antarctica have gotten substantially lower. It's the power of that longer time series of elevation data, akin to what Doug was talking about in terms of time series of fire data, that lets you get a sense of how these big areas are changing through time. So the Antarctic Peninsula and West Antarctica continue to lose ice to the world's oceans, resulting in a primary source of sea level rise. And the lighter blue color in the much larger East Antarctic ice sheet is places where the ice sheet has actually gained mass and increased in height. I will point out, though, that the color scale is asymmetric. So the red areas are losing, say, 5 and more meters of ice per year, whereas the light blue scale caps out at just 50 centimeters per year. So although some areas are growing, it's not nearly enough to keep the ice sheet in balance. And both of the ice sheets continue to contribute ice to the oceans and result in sea level rise. Let's go on to the next slide, please. Another objective for ISAT-2 is measuring changes in sea ice. Sea ice, of course, is formed in the winter when ocean water reaches the freezing point. And these are some figures of what we call the sea ice freeboard. Of course, with imagery, we've been able to measure the spatial extent of sea ice in the polar oceans for decades. But ISAT-2 is adding this third dimension. The freeboard of sea ice is that height of sea ice that's sticking up out of the polar oceans. So the main objective with sea ice data is to, yes, measure the height of everything, but then separate those heights into 2 different categories. Is this an elevation measurement of the open ocean water, or is it the height of the sea ice that's floating in that ocean water? By calculating the height difference, we can measure the freeboard. And here is a series of figures from October 2018 through March 2019 of how the freeboard of Arctic sea ice changed through time. And that's something we've never been able to measure before, at least not in this kind of detail from space. If we go on to the next slide, I believe it's my last one, for a lot of applications, it's the thickness that's really interesting. We can measure these freeboards that are 10, 20 centimeters, but of course, most of the thickness of sea ice is below the ocean surface. So we combine our freeboard measurements with models for snow accumulation and snow distribution that's sitting on top of that sea ice to come up with thickness measurements, which do things like aid in navigation and situational awareness in both the Arctic Ocean as well as the Southern Ocean surrounding Antarctica. And that's what I had to say. Thanks.
Thanks so much, Tom. So clearly ISAT-2 is critical for understanding the Earth's climate, especially as ice sheets melt and contribute to sea level rise. So we'll get back to that. We're going to move on to our next speaker, who is Chris Orndorff. So Chris is the Senior Manager for Technology Sales at Maxar and has been a pioneer in working with NASA's Earth Science Division to support access to the Worldview 4 products. Chris, you're next. Thanks.
Thanks for having me. And we're really excited to be here today. I'm really excited to showcase some of the new technology that Maxar is going to be putting into its next generation of satellites that are going to join our existing constellation. Can we bring up the slides that I have? Let's go to the next slide, please. So a lot of you might have heard of some of the other companies and organizations that have gone into Maxar today. There's a lot of different pioneering and interesting organizations that have made that up to what Maxar is today. We have this long legacy and large archive of data dating back 20 plus years, starting with satellites that people might be familiar called Ichnos and QuickBird 2, which flew in orbit for 12 to 14 years. So great archives and history that we've still have and leverage today. We're currently operating 4 satellites, Worldview 1, GeoEye-1, Worldview 2, and Worldview 3, which are all very interesting spacecraft in their own ways from both a resolution and accuracy standpoint, and also into the payloads that they carry. Worldview 3 was the first commercial 3-payload spacecraft to be put on orbit by a commercial company. And a few words today I'm going to share around our next generation, and that's going to be the Worldview Legion constellation. And so it'll actually be composed of 6 spacecraft launched into 2 different orbits. So let's go to the next slide. This is how you might know Maxar today, is from our high resolution, and that is a cornerstone of what us as a commercial company have been pioneering and pushing for many years, is this 30 centimeter and high accuracy products that we put out in the marketplace today. You might see it in a lot of your mapping applications, your cell phone, a lot of different ways you might come across our imagery. But there's a lot of other ways that you might not have realized Maxar has been pioneering. Let's go to the next slide. And that's in some more of the environmental and climate applications. And so as I mentioned before, Worldview 3 is a 3-payload spacecraft, and we actually get to see a couple of those different payloads on display here. Starting in the top left, Worldview 3 actually operates not only from the visible to the shortwave infrared in 2 different payloads. And here we can see the shortwave infrared piercing through the haze and smoke over an active fire area. And you can actually see where the active fire is and the burn scars and areas of vegetation that have been burned. Obviously, our entire constellation can be leveraged for doing agricultural and other vegetation studies at high resolution. And we can see that here in the top right with NDVI. And then the bottom 2 applications are really interesting, really around snow and ice cover. As I mentioned before, we have this large archive that dates back 20 plus years. It acts as a high resolution archive and time machine for how maybe snowfields or glaciers might exist in certain areas around the world over that 20 plus year time span. And then finally in the bottom left here, we see our CAVIS payload, which is actually active on the Worldview 3 spacecraft, which is a medium resolution sensor that's mirrored the same capabilities of Landsat that images alongside the other 2 payloads in the high resolution. And so let's just click to the next slide. Here, this is an interesting collection. This was over some of the fires in California from last year. And we can see what does that standard high resolution imagery look like as we collect an active fire. Obviously, in the visible parts of the spectrum, we're looking at the top of smoke and haze, and we can't see much. But as we click through, can we just click one? There we go. now we can see in the shortwave infrared. In the shortwave infrared, we're not subject to the same scattering that we would be in the visible parts of the spectrum. And we can see the burned areas quite obviously. And then we can see the active and very intense heat that is picked up, that we do pick up in the shortwave infrared. And that signature you can see in those bright and multiple colors kind of intensity there in the middle, as well as some of the perimeter where there is active burning going on. So, very interesting from a scientific application, but also an emergency management standpoint. We can go from sensor collection to ground station and process that data and get that data into the hands of individuals to use it within a matter of about an hour. And so let's click through just real quick to see what our next generation constellation has in store. And so we're really excited to be changing some of the ways we're looking at our imagery collection. Typically today, all of our satellites follow a sun synchronous orbit with a 1030 local sun elevation time descending node, except for one, which is WorldView 1. That's in an afternoon orbit. Our future satellite additions will be launched into 2 orbits, 2 into that same sun synchronous orbit that we're used to today, but 4 into a mid-inclined orbit, which will allow us actually collection periods throughout the lighting conditions throughout the entire day, and potentially within mid latitudes, we could be looking at 15 revisits per day with our constellation. So we're really excited about the new collection times that we have available to this, and we'll be continuing to push this new constellation at 29 centimeter resolution. So continuing that very high resolution envelope that we've been pushing for a while. And these will also fly with 8 spectral bands from the visible to the near infrared, mirroring that of WorldView 2 and the main payload on WorldView 3. And so if we click to the last one, just a cool high resolution shot at a very high off nadir of the Crew 2 launch not too long ago. So with that, I will turn it back over. Thank you.
Awesome, Chris. Thanks so much. And it's really amazing the combination of the high resolution and the long record length. I mean, when you think about planetary stewardship, it's that the insights you can gain from that are really amazing. So we'll get back to that in a few minutes. So our final panelist is Pam Sullivan. Pam is the System Program Director for the GOES-R series program and has extensive flight development experience both at NOAA and at NASA. So Pam, looking forward to hearing your remarks.
Oh, thanks, Krista. And it's great to be with everyone today. I'm going to talk a little bit about NOAA's current observing systems and also, very excitingly, our plans for the future that are really just being formulated right now. So if we could go to this charts, please. And to the next chart, please. So folks are probably aware our current system, and NOAA's role, of course, is focused on weather forecasting, although we are starting to think beyond that, as we'll talk about. But our traditional role has been weather forecasting, and of course we do that from 3 different orbit locations. Our low Earth orbit capability is currently the Joint Polar Satellite System, which takes some really nice imagery, but of course it's kind of bread and butter are the atmospheric sounders that feed the numerical weather models that drive our forecasts. In our geostationary orbit, we have the GOES-R series, which of course with its persistent view of the Western Hemisphere can keep a very close eye on severe environmental conditions of varying types. And then at the Lagrange point, L1, we currently have the Discover spacecraft, which has the job of looking at solar wind and also coronal mass ejections from the sun. And I'm sorry, it's really just the solar wind right now. The CME capability is coming in our future. And so for all of these satellites, our LEO, our GEO, and the L1 capability, we are currently working on next generation plans. And can we go to the next chart? And so a lot of our planning right now is going out to our user community. We've really tried to engage thousands of users in all kinds of economic sectors, government agencies, international partners, to understand what we're going to need, not just today in our weather forecasts, but also in the 2030s and beyond, when NOAA's next generation systems are going to be active. And so what has become obvious in the discussions that we've had with the users is the planet is different now than it was when we were planning our last generation systems. So the planet is different and it's changing. And that means our user needs are different and they're growing. So a couple of the things that we've heard from users are related to things like harmful algal blooms. Beach closures didn't really happen, 2 decades ago. But now they happen hundreds of times a year. Wildfires, as you saw from Doug earlier, are growing in size and frequency in this country anyway. The link between air pollution and mortality is really very clearly understood, primarily from satellite records over the last couple decades. We're also seeing climate change make hurricanes stronger and also less predictable. They have periods of rapid intensification that we hadn't seen as much in the past. And then just overall, we hear from our users that their forecast needs are increasing. Whereas 2 decades ago, you were lucky to have a forecast, 3 to 5 days in advance. Now people want 10 to 30 days. And so, those needs, meeting those needs are going to require NOAA to do more. So the next chart. So I'm going to focus on geo because that's where I've really been focusing my time of late, trying to formulate NOAA's next generation geostationary system. And so what we're planning in response to these user needs that we've heard, people still need the imagery for that real-time forecast. They want us to continue the lightning data collection. That is also essential to our short-term forecasting needs. The new needs that we're hearing address some of those concerns that I mentioned on the previous page. So for our next-gen geosystem, we plan on adding a hyperspectral infrared sounder. That data will feed into the numerical weather models and help us make more accurate and longer range forecasts. We're also planning on adding an ocean color instrument that will help us assess coastal conditions, ocean conditions and quality, as well as hazards like harmful algal blooms. And we're also planning to add an atmospheric composition instrument that is really going to help us forecast air quality and then understand the links between air quality and climate. So next chart. And so this is just the graphic of what we think our next generation constellation is going to look like. We are at the very beginning moving into formulation, so I need to add the caveat that nothing's approved yet, but this is the system that we think we need to address all of the user needs that I've discussed here. So we plan to have 3 satellites in geostationary orbit. We'll have the traditional east and west spacecraft as we do now. Those spacecraft will carry the imager, the lightning mapper, just like the GOES-R series does now. Those spacecraft will add the ocean color instruments to provide, good views of both the Atlantic and the Pacific. And those spacecraft will also carry the space weather instruments that we currently carry in GEO. In addition to those 2 traditional east and west observation posts, we're also going to have a spacecraft in the center of the country, and that will carry the infrared sounder as well as the atmospheric composition instrument. And so we're very excited. Like I said, we're just working towards KDP-A a little bit later this year. And I certainly look forward to working with NASA and working with industry and the rest of the community to build GeoXO.
Thanks, Pam. Yeah, it's exciting, and it kind of gets back to something Thomas mentioned this morning about partnerships and how important it is to have a partnership to build out the vision that you have for the GeoXO. So we'll be back to that soon. So I think now we're going to move into a question and answer period. And I want to encourage folks that are listening online to go into your chat and enter questions. Alan's standing by, ready to bring your questions to us. And we look forward to having a discussion. So I've got a few questions to get started, and then we'll see what comes in over the chat. So get those chat boxes working. All right, so first question is for Doug. And, I want to ask about fires, right? So, fires have come up several times today. What are some of the gaps in current observations that are needed to capture new extremes in fire activity?
Thanks, Christa. I think it's exciting to hear the conversation, and the overlap and interest here. Obviously, the NASA-NOAA partnership is really strong, and the JPSS instruments are really now the backbone of our ability to monitor active fires in low Earth orbit. But obviously, we're working closely with some of the commercial partners, and it's exciting to see some of the detail that Chris showed for how the high-resolution commercial sensors give us a chance to really pinpoint some of the fire behavior and the fire line dynamics for an individual fire. I think one of the things that sort of drives what Pam brought up in terms of the user needs, and one of the things that we see in terms of the changing extremes for fires, is this goal to observe fires more frequently. And historically, our low Earth orbit payloads have seen fires every 12 hours, which has provided a really important characteristics of how fires change over the course of, say, day to night. But we're missing some of those most explosive times of fire behavior, like the mid-afternoon, when we haven't historically had coverage except for the geostationary sensors. And so I think, as you've seen everyone today describe, we're always working to put together the available pieces that are in orbit and in plan for us to characterize how the geostationary observations can link up with those polar orbiters and the high resolution space-based commercial systems to try to give us a better picture of what's happening. But it's that fine time resolution and the low latency of data delivery that really drives some of the opportunities and those demands from the community.
Perfect, thank you. All right, I have another question. I'm going to send this one to Tom. So, ISAT-2 is super exciting. You showed examples of ice sheet and sea ice mapping. What are some other new capabilities coming out of ISAT-2?
Yeah, from the vantage point of space, and in particular our orbit that takes us from 88 degrees north to 88 degrees south, we spend lots of time in the polar areas, but we see the rest of the planet as well. We take that data from over oceans and forests, deserts, and cities, and some of the results the science community has been putting out are comparing ISAT-2 elevations of the ocean surface in comparison with the longstanding radar altimetry record, and folding our measurements into those. And perhaps a surprising one also from the oceanographic community is that our green laser light penetrates the water column. We do get a return off the top of the ocean surface, but some of that light goes down through the water column and reflects off both suspended material in the water column as well as the sea floor. We've measured down through about 30 meters of reasonably clear ocean water in some of the tropical oceans. And folks are also using ISAT-2 data to study photosynthetic organisms in the water column and suspended sediment as well. So the oceanographic community has been really interested in it. I'd be remiss if I didn't mention the other laser altimeter on orbit. It's called JEDI. It's on the space station. And while that one's really focused on measuring global vegetation canopy heights, ISAT-2 also is measuring canopy heights. And those two data sets together will give fantastic coverage of both the high latitude forests, where the ISS can't support data collection, along with a really dense coverage that JEDI is generating in the mid-latitudes.
Super cool. Yeah. So, I mean, I think blending multiple assets is a huge area that we're going to talk more about. And even later today in the analytics panel, I'm sure they're going to talk about this a lot. Great. Thanks a lot. So, Chris, I have a question for you. This is, I'd like to know more about the science enabled by Maxar assets, right? So, I mean, I've heard about counting trees and some other really cool stuff. Chris, can you tell us more about how your products enable science?
Yeah, so Maxar's had a great partnership with NGA through various contracts over the years to provide more imagery to the rest of the U.S. government agencies like NASA and NOAA. So a lot of principal investigators and others at NASA have leveraged the Maxar data, either historical, maybe shortwave infrared, or other types of data for multiple studies. A few years ago, we actually also did a blanket purchase agreement direct through NASA to provide Worldview 4 data for its short time on orbit into several different programs. And so the data from Worldview 4 was able to apply to the JEDI program, above, and a High Mountain Asia program to use that data from Worldview 4 in those various programs directly as well. But as always, our data is typically made available through NGA and through the contracts we have there into investigations and individuals at NASA or NOAA or other government agencies.
Great. Well, that's really, really amazing. And some of the programs you mentioned, like above in the Arctic and the boreal forest, as well as High Mountain Asia, looking at glaciers. These are some really critical areas from a climate change perspective. So it's great that you can take the Maxar assets and try to understand what's changing on our planet. Okay, so I have a question for Pam. So you mentioned the ocean color instrument, which is, exciting as a new opportunity for GeoXO. How will that the constellation in the GeoXO benefit from the ocean color work happening with our PACE and our Glimmer missions?
Directly is the short answer. We're really excited to see PACE launch in not too far, and then Glimmer, I think, is in 27. And we're already counting on those measurements to get our users ready. There's a lot of science that's going to come out of that, but the NOAA operational users, they really rely on the record being there for a long time. And they've got a lot of work to do to take those measurements, pull them into their forecast models, and understand how they're going to use them and what it's going to enable them to do in terms of putting out warnings and forecasts. So really just getting that data through the system before the operational instrument is there really gets our users up and running. Not to mention the fact, of course, that those instruments are testing out the technology. And really giving us confidence that we're going to be able to achieve the performance that we're hoping for. So really looking forward to PACE and Glimmer, and then the Tempo instrument, which is another NASA instrument planning to launch next year, is similarly going to be a pathfinder for our atmospheric composition instrument. And do those same kind of things. The technology is kind of proven with the Tempo instrument. And once it's up there and producing, measurements of the atmospheric species, again, our users are going to see that data, understand what they can do, and evolve their models so that they can better forecast.
Great. Yeah, that's really exciting. I mean, it's wonderful to have these, NASA science missions be the pathfinders that inform, NOAA in terms of operational capabilities for the nation. So it's a great partnership, that we've had over the years. And I think, PACE with, the being able to detect different types of plankton and understand different species of phytoplankton is really going to break new ground in our ability to understand the ocean ecosystems more than we ever have. So it's
such a long-standing partnership as well. It goes back to the 70s, really, where NASA put up the first cameras, and then NOAA said, "Hey, that's great. I know how to use that." And really, it's been ongoing ever since then. Within NOAA, we call it research to operations, R2O.
Mm-hmm. Yeah, that's right. And sometimes it's O to R, sometimes the users ask questions and we don't know how to answer them. So, we have to think about what observational platforms and what we need to answer the questions that you mentioned. There's so much demand now for, longer forecasts and other things, and that's a challenge. So. Great. So I guess I have some questions, just sort of opening it up to the whole panel. Sort of riffing off of this partnership idea. NASA and NOAA certainly are collaborating on fire science, but I'd like to hear from all four panelists. What are the key collaborations on fire science, and how can, you mentioned even ISAT-2, has vegetation measurements. Certainly Maxar brings a high spatial resolution. How does that all fit together to enable fire science? So Chris, you want to go first?
Sure, I'd love to go first. I think the depth of the archive around the world that Maxar has is a valuable asset to looking at vegetation over time, especially at a high resolution standpoint. Obviously I mentioned earlier just the applications with looking at receding glaciers and things like that at high resolution as well. But we look to for as many partnerships as we can throughout both industry and the public space. And so typically a lot of our focus around fires is actually on fighting fires and getting imagery maybe to first responders. But the archive and the collections around those fires is immensely valuable for the study of fires and spread and potentially the conditions that led up to those through our archive as well.
Great. Any other panelists want to comment on that?
I'll jump in and just point out a couple of other areas of some ongoing synergy. I think this is, obviously the NASA-NOAA partnership around the study of fires and fire impacts and the sort of interactive ways in which the forecast need is there to characterize how smoke represents a hazard for air quality, and also how smoke changes the atmospheric circulation, cloud formation, and rainfall. Obviously goes downwind and has a big impact in terms of weather maker systems. One of the things I think we're still working there to better understand and constrain is exactly where that smoke sits in the atmosphere. And so some of the new sounding techniques and some of the new systems, including some of the capabilities we have from GEO to look with the systems on the east and the west platforms, actually give us a stereo view of those smoke plumes and allow us to pick off exactly where they sit in the atmosphere. And so that's been some really exciting and maybe unexpected work that's really brought NASA and NOAA together in that partnership. The other part I would mention and throw this over to Tom is that as I showed in my last slide, there are many regions of the planet that are actually burning less than ever before. And so understanding how ecosystems are changing from fire, of course, is really critical, but it's even more important in some ways to understand how those areas that used to burn and are no longer experiencing fires, how are those savannas turning into woodlands or forests and fundamentally changing the nature of savanna ecosystems and others around the planet. And so bringing in that third dimension is really critical if we're going to understand obviously those the vertical aspect of the atmosphere, but also the changes in the vegetation itself.
Thanks, Doug. Yeah, that is a good one, because as fire becomes less prevalent, we should see changes in vegetation height, first from very low-lying shrubs and things, and eventually growing into more mature forests. So I'd point to two things. I'd point to reiterate the power of these time series. Vegetation loss is often very fast through a fire or through logging, but the regrowth is much more gradual. And to measure that, you do need a longer time series. The second piece is that it's great that with LiDAR you can get this third dimension, but by combining it with imagery such as from high resolution from Maxar, you can extend in many regards those individual profiles of elevation to put them into a larger spatial context or broader spatial context to get a sense of how that scene or that plot scale is changing with time. And so looking ahead to future observations, data products and measurement modalities that combine a few of these things together, I think is really going to be where the science needs to go to characterize those changes in the future.
Thanks, Tom. Yeah, that's exciting. I think there's a lot of opportunity here. All right, well, I understand the audience has some questions. Alan?
Okay, the first question is for Dr. Morton. Doug, could you talk about how fire managers are using the data that you shared and what additional data may be helpful to support land managers and decision makers in this sphere?
So just really quickly, I'd be remiss if I didn't recognize that some of the pathfinding work that's been done, first with the MODA sensors and now with the VIR sensors on the JPSS series, has been to make sure that there's a direct pipeline for the downlink of data and the distribution of that information, often within half an hour, to the first responders who need to find those active fires and make decisions on the ground. And of course, that is a longstanding partnership in the US with groups like the US Forest Service and CAL FIRE, but that actually extends worldwide. And so a park manager in Kruger National Park in South Africa gets a text message if there's an active fire detected from one of those systems, just like our US fire management agencies might. Where we're going with this, I think, is really exciting. And you heard Pam talk about it a little bit before, but the idea of our Earth system understanding, enabling some really powerful new insights in this sub-seasonal timescale is a really interesting way in which new observations and new Earth system understanding is going to start to be very, very helpful in making proactive decisions to avoid dangerous consequences. And just one example, obviously you've probably heard, or maybe you're living in California and you've had your power cut. We have seen examples now where weather forecast information is being used to make decisions to limit the risk of fire activity through shutting off power in periods of high wind. And I think the more that we can pinpoint those conditions where fires, if they did start, could get out of control quickly, that really puts us in a new decision space. And it's not just the firefighters we're talking to, it's a broader sector that we're engaging now about how we safeguard our communities and protect natural ecosystems.
All right, thank you, Douglas. A question for Pam. At the AMS, you mentioned room for partner payloads in the GeoXO constellation. Could you elaborate on that some?
Yeah, of course. The center satellite that I mentioned is going to have 2 instruments on it right now, but we're envisioning it really as the same spacecraft bus as go in the east and west, which means that there's room for another, fairly large-sized payload to be put there. And there's been nothing defined yet, so we're very open to what is a good synergistic partner payload for us that could be on a platform for 10 years or more.
Very good, thank you. For Chris, you mentioned a number of payloads, a number of instruments. Eventually, customer base becomes important. And have we seen, or are we seeing, or will we see a transition in customer base for your payloads and your instruments from where the government is primarily the customer to where commercial interests are primarily the customers?
Yeah, obviously from the commercial marketplace, as location-based customers, things like that, mapping users, we see the most demand for high resolution and higher resolution, along with accuracy improvements to that data. So that's typically at the forefront of our investments in the way that we launch and design our spacecraft. I think Worldview 3 is a very unique asset that we launched not too long ago, and I look forward to more use out of that spacecraft. The 3 payloads on that spacecraft, one of the ones that I hear probably the least known in the scientific community is actually the CAVIS payload. It's a very fascinating instrument. It's literally an instrument on the side of the spacecraft of Worldview 3. And the resolution from it is 30 meters. So it has pretty much zero application within mapping or location-based users. But the scientific applications for that payload are fantastic. That payload sees from the visible into the shortwave infrared. And it was literally designed, the CAVIS acronym stands for clouds, aerosol, ice, vapor, and snow. And it was an instrument originally we designed to help us identify the difference between snow cover and clouds both of which have a high albedo, and typically in imagery, a lot of our automated processing might assign snow cover as cloud cover. And so from a mapping standpoint, we want to collect imagery in areas without cloud cover, because typically for mapping, you don't want to see clouds. But snow, while it has a different, while it's a bright feature, might also, be something that's permanent within that landscape, and we still want to image that. So originally we designed it just to isolate those two different types of features. But one of the more fascinating applications that have come out is being able to identify snow cover with that, but it also carries two channels that actually have slight parallax to each other. So you can actually determine some major differences in height. So the differences between a snowfield that's on the ground and maybe a cloud that's at 30,000 feet. So there's a lot more scientific applications, and I hope that today and in general, people will look at Worldview 3 and all the different applications it can serve.
All right, thank you, Chris. Tom, talking about ISAT, you talked about elevation data and getting lots and lots of interesting information. Byproduct data. Have you found out things that you didn't expect to find out about things like tectonic plate movement elevations, volcano elevations, coastal recessions, those kinds of items, not just looking for ice, but seeing other things?
Yeah, in fact, geodetic applications was a primary goal of the first ISAT mission, and they had a significant number of geodesists using that data to look at deformation of volcanoes or changes in height due to earthquakes. We've been on orbit now for 2.5 years, and probably the most, unexpected isn't quite the right term for it, but the field that's got more interest than I would have guessed was the coastal bathymetry. That there is this zone close to the shoreline that's really difficult to get bathymetric measurements because you can't take ships in very safely. And so measuring water depths in that 0 to 10 meter of water depth range is something that's really of interest to the Coast Guard, to USGS, certainly to the military for situational awareness. So that's certainly the biggest one. We have a few users who are using ISAT-2 data to look at volcano deformation, particularly the recent eruption, or the ongoing eruption, I guess, in Soufriere volcano. Yeah, that's an area of study that's just out there. So interested scientists can pick that up, and many of those things are low-hanging fruit that are still on the tree at this point, to use that analogy.
Great. Thank you, Tom.
Sure.
Okay, Pam, I spent a little time in a thing called a battleship up in, I guess, in Maryland. I was really impressed by the amount of data that is pulled in, collated, and then pushed through, kind of like a modified bent pipe, with all your satellite data and how it goes to people all around the world. Are you also integrating data from people like EMUSAT and other agencies into your activities and beginning to share that with non-US counterparts?
Yeah, in general, the weather forecasting is a worldwide phenomena, and we share our data, and we receive data from EUMETSAT, JMA, Korea, ISRO, and India. It's always been a worldwide partnership like that. More than half of the data that actually NOAA puts out to its users comes from other partner sources. So the partners are recognized as a key part of our observing system, and we count on the measurements that they're making. And as you say, we distribute that data ourselves, not only via landlines to customers like National Weather Service, but we also broadcast the data. In the case of the GOES satellites, we do that hemispherically. So, anybody within the view of our satellites in the Western Hemisphere can receive our data with a satellite dish, and that's a key part of NOAA's contribution to the World Meteorological Organization and the commitment to again to get our data out to the world. There's just so many ways that the data is shared. For the numerical weather forecasting models. They benefit from the sounders that fly on our spacecraft, on the DoD spacecraft, on the METS spacecraft. So yes, so definitely we do everything we can to pull in partner data and push that data out to all of our users.
All right, thank you, Pam. Christa, one for you, since you pulled this entire group together. Everybody's talked about lots of different kinds of data, and old data, new data, data to come. From an overall overview point of view or standpoint, what's being done to layer all this data, time phase the data, and interlace it so that we're able to pull together a congruent picture of what's going on either worldwide or within certain areas from all these different kinds of instruments, all these different kinds of programs, so they're not operating as silos?
Well, this is such a great question. So thank you to whoever submitted it. As this panel has showed, there are so many different assets, different resolutions, different time periods. And one of the things that we are especially interested in as a planetary stewardship mandate is really to develop what we call climate data records, right? So we have programs at NASA where we synthesize data together from multiple assets to answer certain questions. And we're working on a project right now that we're calling the Earth Information System, where we are pulling data from multiple satellites as well as ground-based assets, which we haven't even talked about today, to provide answers to important questions like, is the water cycle changing? Is sea level rising? We have a whole NASA sea level change science team that is focused on synthesizing data from ice sheets, as well as ocean data and geodetic data to answer these questions. So I think it's a really important element of NASA's and our partners' programs to think about how we bring the data together, how we understand trends, and how we can predict the future based on our understanding of the past and present. Alan, I'm not hearing you.
Now you will. I was mumbled in under my breath on a few things because it was really, really interesting response. And knowing that kind of thing is being done to put things together is great. We do have an interesting question I was just reading, and this is what I was mumbling about for Mr. Orndorff. And is it possible, Chris, or do you have programs where students can come to you and do projects with you with your imagery, or come and bring you suggestions on things to do with your imagery? Some kind of, not actually an intern thing, but some kind of external outreach or internal inreach to work with students.
Yeah, and we do. So obviously we have a lot of relationships and partnerships through NASA that a lot of PIs and others can get data and access to our archive through a lot of those avenues. And then we also have the Maxar Foundation, where we actually provide, there is some outreach and data that is provided directly to universities and students through that channel as well. So I would say if somebody is maybe a university or an affiliate through NASA working on a specific area, that relationship through NASA and NGA is a great way to get access to a lot of our data. And then if not, the Maxar Foundation, I would definitely recommend people check that out for access to some of our data that we also provide for some humanitarian causes and other crises around the world as well.
Superb. That's actually much more than I expected. That's wonderful. So we're at the end of the period. I think we had some tremendous information exchange, and I certainly learned a lot of stuff. And so Christa, thank you for pulling together the panel and moderating panel. Thank you very much for going through this with us.
Thanks. It was a great opportunity. And hope you all enjoy the rest of the symposium.
All right. So thanks to our day one sponsors, and we should have them up here momentarily. But if we don't, anyway, it's time for us to end our day or end our morning. We're going to take a break until 1:10 p.m. Eastern. And at 1:10 precisely, or maybe 30 seconds after, 30 seconds before, we will present an award for a very successful mission, and something you guys have all read in the newspapers and in the blogs. So thank you very much. We'll be offline until 1:10.